In this video, we revisit impulse and momentum. Momentum is represented with capital letter P and is defined as the product of mass and velocity. Momentum is a vector. It's a product of the mass, this is a scalar, and velocity vector, this is velocity. So the direction of momentum is given by the direction of this velocity vector. So we can also picture momentum as mass in motion, mass in what? Motion. Looking at this, you see that the unit of momentum will be kilogram meter per second, because mass is in kilogram and velocity is in meter per what? Second. Let's say a fly flies at a velocity of 20 meter per second and a car moves at this speed also 20 meter per second. Which of these do you think will be easier to be stopped? You see that the fly will be easier to be stopped. So the fly has lesser momentum than the car moving at this speed. Of course, you now see that the speed are the same. So the car is more massive than the fly. Looking at this formula for momentum, you see that when the mass is high and the velocity is high, so you see also that the momentum will be what? Will be high as well. So the car has higher mass than the fly, even though they have the same speed. So it then means that the car will have greater momentum than the fly. So the higher momentum a body has, the harder it will be for it to be stopped. Okay, so now let us look at relationship between momentum and impulse. Impulse is like a blow. When a large force acts on a body for a very small time, it is called impulse. So impulse is the product of force and time. So from Newton's second law of motion, Newton's second law says that F is ma, the product of mass and acceleration. So acceleration, we know, is change in velocity upon change in time. So if we call this equation 1, we can get another equation and relate it with this. So we can have that F can be written as change in mass, the product of this. So, and of course this is the momentum we are talking about. So this is change in momentum. Of course, momentum is product of mass and velocity. So this will be what? Change in time. So if we cross multiply, of course, you now see that change in momentum will be given as product of force and time. So let's call this equation 2. If we compare equation 1 and 2, you now see that impulse, which is given as the product of force and time, is same thing as the change in momentum. And what is this change in momentum? This change in momentum is the final momentum minus the initial momentum. So which we can write as this. This is mv final minus mv initial. So this is basically relationship between the linear momentum and impulse. So you see that momentum is, the unit is kilogram meter per second. So the unit of impulse is, this is force, which is in Newton, time is in seconds. So the unit of impulse is Newton seconds. We now see that kilogram meter per second is equivalent to Newton seconds. So the unit of momentum will be the same as that of impulse, and dimensionally it will still be the same. So let us solve some problem to illustrate this. So let us solve this example problem. A body of mass m hits normally a rigid wall with velocity v and bounces back with the same velocity. The impulse experienced by the body is dash. So let's make the diagram. This is the wall and a body of mass. Let's say this is a ball. This body hits this wall with a velocity v. So the initial velocity is v, and it bounces back with the same velocity. Of course, velocity is a vector, and since it is bouncing back, the final velocity now will be opposite to that of the first one. So this will be minus v. So this is the final velocity v, and this is the initial velocity u. So the question says the impulse experienced by the body is dash. So how can we now picture the impulse? So to solve this, we say that impulse is rate of change of momentum, change in momentum. And momentum, okay, the change in momentum, we can write it as, this is impulse, so we can write it as change in momentum. So this will be the final momentum minus the initial momentum. Final momentum minus the initial momentum. Okay, so to find the final momentum, this is final momentum, this is mv final. So we have the mass is constant, the body has mass capital M, so we have m times the final velocity is minus v, so that we have this becomes minus mv. So to find the initial momentum, which is this, initial momentum will be the mass is still constant m, and the initial velocity is given as v. So this is mv. So to find the change in momentum, p, of course we see that impulse is change in momentum. So we have it as, this becomes final momentum minus initial momentum. So change in momentum is final momentum minus initial momentum, and this is the final momentum and this is the initial momentum. So the final momentum is minus mv and the initial is this, so we have minus mv, and this gives us minus 2 mv. Of course, you see that the direction of the velocity, final velocity, is the same as the direction of the momentum vector. That's why we're having negative here. So if we take the magnitude of the change in momentum, we now have that this is 2 mv. So option C is the correct answer. Now let's solve another problem. So this question says a 50 kg object is moving at 18.2 meters per second when a 200 Newton force is applied opposite the direction of the object's motion, causing it to slow down to 12.6 meters per second. How long was this force applied? So to solve this, let's draw the diagram to illustrate this motion. So we have a 50 kg object. So if this is the object having 50 kg is moving at this velocity, so the initial velocity of the object is 18.2 meters per second. When a force of 200 Newton is applied opposite the direction of this object. So if a force F 200 Newton, of course this will be opposite to the direction of this motion, so it will be negative 200 Newton, causing it to slow down to, this slows down to 12.6 meters per second. Of course this becomes the final velocity. The question says, how long was this force applied? How long? So this is asking about the time. So using the impulse momentum relation, we say that impulse Ft equals change in momentum, and change in momentum is giving us this. This is change in momentum. Okay, so utilizing this formula, we now see that F is giving us minus 200 times, this is the time we are looking for, this is M, V is 12.6 minus U is 18.2. So if we make T subject of the formula, from this we have it as, of course the mass is given as 50, so this will be 50 kg. So you have 50 brackets 12.6 minus 18.2 upon minus 200. You see that the mass M is given in kg, so we don't need to do conversion. The mass is in its SI unit. So if we do this math, we now have that the time equals, so the time equals 1.4 seconds. So let's solve another problem. So this question says, when accelerating from a stooped position, a 1000 kg car is subjected to a constant force of this 6.1 times 10 to the power of 3 Newton. Using the linear impulse momentum principle, determine the speed of the car 8 seconds after start. So solution, we see that this car was initially at rest. This is the car, it was initially at rest, so the initial velocity is 0. So using the linear impulse momentum formula, impulse is change in momentum, which is this, and impulse is product of force and time. So we have that the force given, of course what we are looking for is the final velocity, because the initial velocity is already 0 because the car is at rest. So this is Ft equals mv, and we are looking for v. So if we make v subject of formula, we have Ft upon m, and F is given as 6.1 times 10 to the power of 3, and time is 8 seconds. Of course it's in its SI unit, so we don't have to do any conversion. So the mass is still in its SI unit. This is 1000 kilogram. So if we do this math, we have, approximately 48.8 meter per second. In the next video, which will come shortly, I will be discussing the conservation of linear momentum. If you have really enjoyed this, subscribe to this channel for more video updates like this. You locate the subscription button below, share it with your friends.